Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to optoelectronics devices and systems, and we're discussing about the band gap modulation or the manipulation of the energy difference between the valence band and conduction band. So far we have discussed the methods of compound semiconductors or alloy semiconductors and doping extrinsic semiconductors. So in this video we'll be discussing about the temperature and pressure, the change of temperature, surrounding temperature and pressure, that method of band gap modulation. So before we go in detail about this, we know that band gap or forbidden energy gap is the energy difference between the valence band and conduction band, where valence band is the energy associated with the outermost orbit, which is maximum, and that energy difference is called as forbidden energy gap. Why this is important? Because the basic operating principle of optoelectronics, which involves the use of semiconductors for the design of almost all the important components, it involves the excitation of electron from valence band to conduction band and then from conduction band to valence band with the absorption and emission of photons. So initially the valence band is filled with electrons at room temperature. When light falls on the material, the electron in the valence band, they absorb the light photons and they excite or they move to the conduction band, leaving behind a vacant electronic site. It creates an electron hole pair. After a fixed period of time, the excited electron in the conduction band again drops down to its original position with the release of the photon. So this is the basic principle of operation of optoelectronic source and detector. So the main thing here is the energy difference between the valence band and conduction band. Okay. So if we can adjust this energy gap, if we can bring close down this energy gap, minimize this energy gap, then this transition between valence band and conduction band, it will be smooth. So different methods are used for adjustment of this band gap energy, and that process is called as band gap modulation. Okay, where the amount or magnitude of the semiconductor material's band gap is adjusted according to the requirement. Also, band gap energy affects the operating wavelength or frequency of the light signal, the operating frequency and wavelength. So that's why also it is very important. So different methods are used. So far we have discussed the alloying method, the compound semiconductor method, and the doping method, extrinsic semiconductor method. In this video we are going to discuss about the use of temperature and pressure, how changing the surrounding temperature and pressure can affect the band gap energy. So here before we discuss about effects of temperature and pressure, we have to be familiar with the concept of crystal structures. We know that semiconductors, they are crystalline in nature. So the structure of the crystalline solids, it is studied in terms of space lattice and unit cell. So a space lattice is basically an imaginary combination of lines or combination of geometric points which forms a net-like structure. So it basically divides a space into equal identical volumes, and unit cell is the smallest representative of the crystal structure. We have already covered this in physics of semiconductor devices. You can watch that video also. So there are many types of crystal structure, but three basic types are simple cubic type, okay, where there are molecules, atoms or ions at the 8 corners of an imaginary cube. Then we have the body centered cubic, which is basically simple cubic along with an atom or molecule or ion at the center of the cube. And then we have face centered cubic, which has the simple cubic with additional atoms at the center of each of the 6 faces of the cube. So why I am discussing this? Because temperature and pressure change affects the crystal structure, okay, the arrangement of the crystal structure because of the vibration of these atoms. Because when temperature and pressure is changed, all these atoms which were located at their original position, initial position, they start oscillating or vibrating. So when that happens, their position is changed and this leads to a change in the band gap energy. So here, when temperature and pressure is changed, under the influence of temperature and pressure, the atom, it starts oscillating around their mean positions, their original positions. This leads to a change in the size of or arrangement of the crystal lattice because of the oscillation of the atoms around their mean position. And that leads to a change in the forbidden energy gap, because forbidden energy gap is everything about the position of the atoms and the electrons present in the outermost band, okay, the valence band. So when there is a change in the position of the atoms because of their oscillation, the position of the electrons which in the outermost orbit of each atom in the valence band, that also changes, and that leads to a change in the band gap energy. So that change in band gap energy with respect to temperature, only temperature, is given by this equation, where the band gap energy at a particular temperature capital T is equal to band gap energy at 0 Kelvin minus alpha into T square by T plus beta, where alpha and beta are constants which depend on specific materials. So here is a table where we have the band gap energy at 0 Kelvin, alpha and beta values. For silicon it is 1.170 band gap energy at 0 Kelvin, alpha value is 4.73 into 10 to the power minus 4, beta is 636. For germanium it is 0.744, the band gap energy at 0 Kelvin, alpha is 4.774 into 10 to the power minus 4, beta value is 235. For gallium arsenide, which is a compound semiconductor, which is 1.519 band gap energy, and alpha value is 5.405 into 10 to the power minus 4, beta is 204. Indium phosphide, it is 1.421, 3.16 into 10 to the power minus 4, the alpha value, beta is 162, and this is like that, okay. So this is the Eg at 0 Kelvin, band gap energy at 0 Kelvin, and alpha and beta. So if we put these values in this equation, we'll get the general value of band gap energy at a specific temperature T in terms of Kelvin. So this is the relationship with respect to temperature. And for all these semiconductors in this table, the temperature coefficient, that is the rate of change of band gap energy with respect to temperature, is negative. This is about the temperature relationship. For pressure, the effect of fundamental band gap is both positive and negative pressure coefficients. The same reason with change in pressure also, there is a vibration of the atoms around their mean positions, which leads to a change in the arrangement of the crystal structure. It affects the space lattice, and as a result it also obeys a similar mathematical relationship with respect to pressure also. And here the effect of pressure in terms of the pressure coefficient for different semiconductors, it is like this. For silicon, the nature of the pressure coefficient of energy band gap is negative, okay, where dG by dP it is minus 2.40 into 10 to the power minus 6. For germanium it is positive, okay, it obeys direct relationship, that is, with increase of pressure the band gap energy will increase, with decrease band gap energy will decrease. Gallium arsenide also same, positive pressure coefficient, that is, with increase of pressure band gap energy will increase at this rate, and with decrease of pressure it will decrease at this rate. Only for silicon it obeys negative, that is opposite relationship, that is, with increase of pressure the band gap energy will decrease, with decrease of pressure the band gap energy will increase, opposite relationship. So this is how temperature and pressure it affect the band gap energy values, okay. For pressure also it obeys a similar mathematical relationship, and the reason is also the same, that is, with temperature and pressure the atoms present at each position in the crystal lattice, crystal structure, they start vibrating about their mean positions, their original positions, as a result of which there is a change in the crystal structure, the space lattice. As a result of that we have a change in the band gap energy because of change in the position of the atoms, okay. So this is the temperature and pressure change method of band gap adjustment, band gap energy adjustment. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to engineering, science and technology. Have a great day. Thank you very much.